Okay, so we continue with the topic of the previous video, which is topology. However, we're going to give a different spin to it. Okay, you remember the definition of topology, right? So you have a set X. A topology is a collection of subsets of X called open that contains the empty set, contains X itself. It contains the intersection of any two sets that are open. So for any two sets in the topology, their intersection is the topology. It also contains the union of any number of sets, any collection of sets in the topology, so any union of open sets is open. We saw in the video that whenever you have a metric space with a metric t sub x, there's a natural topology associated with it, which is you consider the open sets according to the metric, right? So, which really means that for all x in A, there exists a positive radius such that Bx delta is contained in A. Right, so these are the open sets according to the metric D sub x, and these subsets form, this collection of subsets of x forms a topology in this sense. Okay. So given that we have a metric, it's sort of natural to imagine that maybe we have more straightforward definitions of what open sets are, or about these other concepts such as closed sets, closure, interior, boundary, and accumulation set or derived set, right? So we want to give those concepts descriptions in terms of the metric. We have already done that for closed sets because we said that a set is closed, well, meaning its complement is an open set according to the metric T sub x, if and only if any convergent subsequence, any convergent sequence inside the set has a limit in the set as well. So what about the other concepts, right? So here's what I want to do. I want to give, for each one of those concepts we had in the previous video, a metric formulation. And let's start with the interior because it's the easiest case. So remember that the interior is just the union of all open sets contained in S. So it's always an open set. Well, I forgot to prove this last time, so let me leave as an exercise. S equals its interior if and only if S open, and that's in this setting, okay? The setting of general topology, point side topology. It's sort of simple, but let me say quickly how it goes. If S equals interior, then S is open because there's a union of open sets. So the interior is always open, as we noted last time. If S is open, then one of the sets in this union is S itself. Therefore, S, the union of all these guys contains S, but it's also contained in S. So the union equals S when S is open. Okay, but let me come back to this. I want to give a metric definition of this, right? So what is the interior in terms of the metric? Well, we will show now that it's exactly the set of points such that there exists a delta with the whole ball of radius delta contained in S. So this reminds you of the definition of an open set for sure, right? So an open set is precisely a set where all elements have such a ball. In an arbitrary set S, the set of points that have such a ball is the interior. So that's what the proposition is saying. How do we prove this? Well, it's really simple, right? So first of all, notice that for all x in S with this happening, right, for some delta, I'm not going to write it here, but suppose you have a point in S for which there exists such a ball, right? So then we know that Bx delta is an open set contained in S. And the interior is the union of all such open sets contained in S. So let me say Bx delta shows up in the union that we wrote above. Therefore, well, if a set is one of the sets in the union, it's contained in the union. And the union, by definition, is the interior, right? So if a point has its protective bubble inside of S, then it belongs to the interior, right? Because X is here, contained in the ball, which is contained in the union, which is exactly the interior. So X belongs to the interior. Okay, so that shows that any point satisfying this has to be in the interior, right? So on the other hand, let me now write another direction. So take an S that belongs to let me call it X prime, actually. Take an X prime that belongs to the interior. The interior is a union. So let me erase all of this. Okay, so take a point that is in the interior. So that means that if a point is in a union, it has to be in one of the sets of the union. Right? Now, since A is open, according to the metric, we have that there exists a positive delta such that Bx delta is contained in this A, but this A is also contained in the union, which is contained in S. Okay, so we could even be more, kind of just skip the step and just say, well, we know that this A that we picked out of the union is an open subset of S, so we have this. And therefore you see that because, sorry, I forgot the prime here, right? Because X prime is a point of the interior, we could find a protective bubble around it that's entirely contained in S. And therefore, any point in the interior satisfies this condition here. What did we show, right? So I just proved that any point in the interior is in the set. It has a protective bubble. We also showed that any point that has a protective bubble, well, that protective bubble is an open set that shows up in this union. Therefore, the point belongs to the union. So the two sets are the same, right? Any point that belongs to the interior belongs to the set. Any point that belongs to the set belongs to the interior. And we're done with this proposition. Okay, so that's only one of the concepts that we had last class. So we actually had 4 concepts in the end. And so let me go to concept number 2, which is a closure. So the closure has a somehow even nicer description. So I also have an exercise, right? So I should have said that just like last class, S is a subset of X throughout this lecture. So the closure is the intersection of closed sets that contain S, right? This is the definition, the general topological definition. In our setting, what we're going to show now is that this definition translates into taking all points to the space X. There are limits of sequences contained in S. Again, what happens if S itself is closed? So if S is closed, then we know that all sequences contained in S have limits in S. Therefore, if S is closed, it's equal to its closure. Actually, you have an exercise that's really exactly like this one, which says that S equals its closure if and only if it's closed. Well, we know that the closure is closed, so if this is true, then certainly S is closed. On the other hand, if S is closed, it must be the smallest closed set containing S, right? No set containing S can be smaller than S. And so S is the smallest closed set containing S, therefore it's equal to its closure. Right, but so this holds in this general setting. what I'm saying in the setting of metrics is that we have this description by sequences, right? So why is this a metric description? Well, because convergence is given by the metric, right? Okay, and this is also related to what we proved before, right? If a set is closed, then all sequences have limits in the set. So that's saying, okay, to get the closure of S, all you need to do is to consider the points in S and the points that are limits of sequences in S, right? So it's clear that any point that's already in S is the limit of a sequence of points in S. That's just a constant sequence. Just if X belongs to S, you can just take X1 equal to X, X2 equal to X, and so on and so forth. But there are other points, kind of that maybe do not belong to S, but they're limits of sequences. Once you add those, you have the closure. Okay, how do we prove this? Again, we're going to have two directions, right? So first I'm going to show that any point that's the limit of sequences in S has to belong to the closure. And then I'm going to show that any point of the closure is a limit of sequences of a sequence in S, right? So take a point that's a limit of a sequence in S. Now, how do we prove that this point belongs to the closure? So the closure is an intersection. I want to prove that X belongs to the closure, but that's the same thing. How does a point belong to the intersection? It has to belong to all sets. For all F containing S closed, X belongs to F. So that's what we want to prove. But okay, what do we have, right? So we have that X sub n is a sequence of points in S, and S is contained in F, right? So if you take such an F, X sub n is a sequence of points in F. Therefore, since F is closed, we know that the limit of the sequence X sub n, if it exists, also belongs to F. But this limit is exactly the point X that we're talking about, right? So again, X sub n is a sequence of points in S. Therefore, it's also a sequence of points in F, right? For any F like this. A sequence of points in F must have its limit in F. Therefore, X belongs to F. Now, F is any closed set containing S. Therefore, X belongs to all closed sets contained in F. F is any closed set containing S. Therefore, X belongs to all closed sets containing S, and it must then belong to the intersection of all closed sets containing S. That is, X belongs to the closure. So any point that's a limit of sequences must belong to the closure. What about the other direction? Is it true that any point in the closure is a limit of sequences? So let's show that that's the case now. So and for that, we're going to use a result from last class. We know that there's an alternative description for the closure, even in the realm of general topology. So we know that for any open set containing X, the intersection of S and A must be non-empty. Now, I don't care about all open sets, I care about a specific family of open sets, which it's balls, just open balls. Right? Because these sets are open, therefore, if any open set containing X intersects the set S, it must be that all open balls containing X intersect S. But now we're done, right? So because we know from something we saw in the first video in topology, and it's also an exercise in the notes, this condition implies is actually equivalent to the fact that there exists a sequence of points in S that converges to X. Therefore, any point in the closure has to have its convergence sequence coming from S. So again, what did we show, right? Right now I showed that any point of the closure is a limit of a sequence of points in S. I had already shown that any point that's a limit of a sequence of points in S has to be in the closure. Therefore, an element belongs to this set if and only if it belongs to this set. The two sets are equal. Okay. Third theorem, not third proposition if you want. It's just a corollary of this one. It's about the boundary, right? You remember that the boundary is an intersection of the closure of S with the closure of the complement of S. And I'm just going to write it here. Let me erase the proof. And you can start thinking about, okay, the complement here is related to the set X, right? To our universe, so to speak. Okay. So points in the closure are limits of sequences inside S. Points in the closure of the complement are limits of sequences in the complement of S. Therefore, points in this intersection are precisely the points in X, such that there exists a limit, a sequence inside S, and another sequence outside S, such that X sub n converges to X, and X sub n prime to X. So this is related to this picture that I showed you of the boundary, right? Imagine S is a set, X lies here, the other side is S complement. So being on the boundary means that you can be hit by sequences coming from both sides. I'm not going to prove this because, as I said, it's a corollary of the previous one, right? So saying that this sequence exists means that X belongs to the closure of S. Saying that the sequence exists means that X belongs to the closure of S complement. So this is just straightforward. Okay, and now there's the case of accumulation, the derived set, the set of accumulation points. And that's even easier. Well, I mean, that's easier of all, even though we had a little bit of trouble with this concept, right? So let me, I'm going to rewrite the definition. So S prime is the set of all points in X, such that for all open sets containing X, A intersection S minus X is non-empty. Right, so if you just have S here, that's the closure by a theorem we saw last time. So a point is in the closure if any open set containing it intersects S. This is a stronger thing, so it says that any open set containing X intersects S minus the point X itself. So, okay, what's the, and my claim now is that this is exactly the same thing as saying that for, these are the points for which there exists a sequence of points in S minus X that converges to X. Right, so the proposition is that these two things are the same. And one direction is saying, okay, so suppose that a point belongs to S prime, so all open sets, blah, 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 blah. So that means that for all positive delta, the open ball of radius delta around X, which is an open set, must intersect S minus X. And now we use again this result that we used when talking about closures, right? This condition is exactly equivalent to X being a limit of a sequence of points in this set. Right, so this is an if only if. Okay, now what? I want to argue that, okay, so if X belongs to the derived set, then it's a limit of sequence of points in S minus X. How do we go in the other way? Okay, this is an if and only if, right? Now, observe what happened here. So say that X is a limit of sequences. So we know that any open ball from here, any open ball containing X must intersect S minus X, right? So let me redraw the arrows. It's going to look a bit funny because I'm doing the proof from the bottom up, right? So one, I can do it like this. So now, okay, so now how do we prove this condition? If I take an open set X, we know that A contains an open ball, and this open ball intersects S minus X. Right, so because A is open, it contains an open ball centered at X, right? It's open and X belongs to it, so contains an open ball centered at X. This open ball must have non-empty intersection with S, but then the same holds if I replace the ball by A, right? If I take a larger set here, and the intersection was already non-empty before, this can only be larger. So we're done, right? So if X is a limit of sequence of points in S, then for all delta, the open ball of radius delta around X intersects S minus X. And then for any open set, what we're showing here, because the open set contains a ball around X, the open set must intersect S minus X. Therefore, if this is true, right, so if the proof is, if this part is 1, 2, 3, if 1 is true, so if X belongs to the set, it must be that X is an accumulation point. Okay, so we're done with this part. And that's it for this video. Thank you.